Alright guys, so what we're going to look at in this video is total internal reflection. This is one more expansion on our idea of reflection and refraction to show how light can either reflect or refract based on its incoming angle. Okay, so the important thing here we're going to look at is, let's say we have a material that is higher density than another medium, right? So in this case we're going to use something like water and air. Okay, so if you remember, we have an index of refraction of air. We're going to call this, I'm just going to call it N air is equal to 1, and NW is equal to 1.33. So if you remember, we have right here when we traveled from air to water, what we did is we refracted, and so this angle got smaller with respect to the normal from when traveling from air to water. But if we did this the other way, let's say we traveled from water, let's make this a little neater, we traveled from water to air, we start with some angle, we'll call this theta 1. When we leave, we'll have a larger angle, theta 2. Okay, theta 2 will be greater than theta 1 when I'm traveling from water to air because my index of refraction is going down, right? So remember, my index of refraction here is going to go down, so my angle is going to increase. Well, there happens to be a certain point, since theta 2 is greater than theta 1, there happens to be a point, I'll put this in another color here, where if I income with some angle, call this theta, you know what, I'm going to call this theta C, this is some critical angle. If I am incident with this angle at the surface, well, what's going to happen is theta 2 has to be greater than theta C, but by a certain factor. But if I do this, I'll have more than 90 degrees on my angle, and so this will become reflection. No light will leave, even though it's coming incident on the surface, no light will actually leave into the other medium. So this will produce something called total internal reflection, right? So the way we look at this, let's go ahead and take Snell's law again. We have N1 sine theta 1 is equal to N2 sine of theta 2. And I want to see where this is going to happen. So pretty much the place where this is going to happen is where my theta 2 is equal to 90 degrees. Okay, so this is going to be my critical angle, that when I income with this angle, it's going to be 90 degrees. And anything greater than this angle, so anything greater than my critical angle, is just going to reflect inside. It's not going to refract anymore. So if we look at this, sine, so we're going to have my N1, this, my index of refraction for air is going to be 1. And this is going to be sine of my critical angle. This is what I'm looking for. Well, here for water, I have 1.33. And the sine of 90 degrees, this is just 1. Okay, so pretty much I have, oops. So for my sine of theta 2, I have 1.33 over 1. Okay, so if we do our same trick from last time and I take the inverse sine of both sides, then I have the sine inverse of 1.33. So if we look this up in our calculator, so we have sine inverse 1.33. Oh, sorry, I did this backwards. Yes, I got an error on my calculator. So I have this backwards here. My theta 1 should be water because I'm starting in the water and then I'm ending in air. Sorry guys, I got that backwards. So let's go ahead and come here. And this should be 1 because I'm moving into air from water, right? So 1.33. So this actually should be, of course, my sine of theta can never be greater than 1. It always has to be less than 1. So this is 1 over 1.33, which should be go ahead and okay. This is 0.75. 0.75. Okay, and this is equal to about 48.75 degrees. So pretty much if I am incident at 48 degrees, I'll internally reflect instead of refract. I'll produce this total internal reflection on my surface. And anything greater than this value, right? So if I am incident with 50 degrees or 60 degrees, well, this won't produce refraction anymore. What it'll do is it'll only reflect.